On July 16th, 1994, astronomers watched the solar system reveal one of its deepest secrets. A comet called Shoemaker-Levy Nine had been torn apart into 21 separate fragments after passing too close to Jupiter. Over the next 6 days, those fragments slammed into the giant planet one after another. The explosions were almost impossible to comprehend. The largest impact released millions of megatons of energy and left a dark scar in Jupiter's atmosphere larger than the Earth itself. For months, the mark remained visible. What unsettled astronomers was not what happened to Jupiter. It was what might have happened if Jupiter had not been there. The comet had entered the inner solar system. Jupiter intercepted it, and suddenly, scientists were forced to confront a possibility that had been quietly hiding in plain sight. Earth may owe its existence to a planet most people never think about. Jupiter contains more mass than every other planet in the solar system combined. Its gravity helped shape the asteroid belt. It influenced where the planets formed. It altered the materials that eventually became Earth. Some researchers now argue that without a Jupiter-like planet, complex life may struggle to survive long enough to evolve at all. Meanwhile, one of Jupiter's moons is being torn apart by gravity and covered by constant volcanic eruptions. A storm larger than Earth has been raging in its atmosphere for centuries, and the sun itself does not sit perfectly still. Jupiter is so massive that both objects orbit a shared center of gravity in space. The more scientists learned about Jupiter, the harder it became to see it as just another planet. If you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. To understand this, we need to go back to the birth of Jupiter itself. Imagine drifting toward Jupiter from the darkness between worlds. As the striped globe swells across your view, something strange begins to happen. The closer you get, the harder it becomes to answer a simple question. Where does the planet actually begin? We are used to worlds with edges. Earth has oceans, mountains, and solid ground beneath our feet. Mars has deserts and canyons. Even distant icy moons possess surfaces you could, at least in theory, stand upon. Jupiter offers no such boundary. Its outer atmosphere simply grows thicker and denser, layer after layer, until the distinction between sky and planet starts to lose meaning. What we call Jupiter is composed overwhelmingly of hydrogen and helium, the same elements that dominate the Sun. Roughly 90% of its molecules are hydrogen, while most of the remainder is helium. Because of this resemblance, astronomers sometimes describe Jupiter as a failed star. The phrase sounds dramatic, yet it reflects a real physical relationship. To ignite as a true star, an object must gather enough mass for its core to become hot and compressed enough to sustain nuclear fusion, the process that powers the Sun. Jupiter never reached that threshold. It would have needed roughly 80 times more mass. Instead, it remained suspended between categories, too massive to resemble any rocky planet, yet far too small to become a star. Its scale is difficult to absorb. Jupiter contains more than 300 times the mass of Earth. In fact, it possesses more than twice the combined mass of every other planet, moon, asteroid, and comet orbiting the Sun. The rest of the solar system, when measured against Jupiter, begins to feel surprisingly lightweight. Yet despite this enormous bulk, Jupiter spins with astonishing speed. One full rotation takes only 9 hours and 56 minutes. A world large enough to contain more than 1,300 Earths completes a day in less than half the time required by our own planet. That rapid rotation shapes everything we see. Warm gases rise, cooler gases sink. The planet's spin stretches these movements into immense bands that wrap around the globe. From far away, they appear as orderly stripes. Up close, they are rivers of atmosphere flowing around a world with no surface beneath them. Deep below the visible clouds, conditions become increasingly extreme. Pressure climbs relentlessly. Hydrogen, the lightest element in existence, is squeezed into forms impossible on Earth. First, it behaves like a liquid. Far deeper still, it begins acting like a metal capable of conducting electricity. Meanwhile, Jupiter continues releasing energy left over from its own formation. Even today, after roughly 4.5 billion years, it radiates significantly more energy than it receives from sunlight. The giant is still slowly giving off ancient heat stored during its birth, and that birth changed everything. Long before Earth existed, Jupiter was already reshaping the architecture of the young solar system, establishing the gravitational framework within which every future world would emerge. Long before oceans gathered on Earth, before continents drifted, before any rocky planet had settled into its future orbit, a race was already underway around the newborn sun. Dust collided with dust, pebbles merged into larger bodies. Everywhere, material was trying to become something more. One object gained an advantage almost immediately. Within roughly 3 to 4 million years after the sun began shining, Jupiter emerged from the surrounding disk of gas and debris. In cosmic terms, this was astonishing speed. Planet formation is usually a gradual process, yet Jupiter reached a critical stage while the young solar system was still crowded with raw material. At its heart, a dense core of rock and ice accumulated through accretion, a process where countless collisions allow small objects to combine into larger ones. The growing core eventually reached a mass of roughly 10 Earths. That threshold changed everything. Gravity took over. Hydrogen and helium from the surrounding disk began falling inward faster and faster. The more gas Jupiter gathered, the stronger its gravity became. The stronger its gravity became, the more gas it attracted. A runaway process had begun. Within a relatively short span of time, Jupiter swelled into the giant world we recognize today. But this opportunity was temporary. Young stars are energetic and turbulent. Powerful streams of charged particles flowed outward from the infant sun, gradually stripping away the vast disk of gas surrounding it. Once that material disappeared, the era of gas giant formation effectively ended. Any world that had not already gathered enough mass lost its chance. Jupiter arrived first. That timing mattered enormously. Every planet that formed afterward inherited a solar system already shaped by Jupiter's presence. Venus assembled within an environment Jupiter had altered. Mars grew within conditions Jupiter had influenced. Earth itself emerged inside a gravitational landscape that no longer resembled the one that existed when the sun first ignited. Modern computer simulations reveal just how sensitive this process was. Shift Jupiter's formation forward or backward by only a few million years, and entirely different planetary systems appear. Some simulations produce no stable inner rocky worlds. Others place them in unfamiliar orbits. In many cases, planets resembling Earth never emerge at all. As Jupiter grew, its gravity continuously redirected material throughout the disk. Some objects were pulled inward, others were scattered outward. Many were removed entirely. What might appear as disorder from a distance was being guided by an increasingly dominant influence. The young solar system had acquired its largest architect. Researchers suspect Jupiter's core formed rapidly enough to preserve material dating from the earliest moments of solar system history. Tiny chemical signatures trapped deep inside the planet may remain largely unchanged after billions of years. This possibility drives much of the interest surrounding the Juno spacecraft, whose measurements continue probing beneath Jupiter's cloud layers in search of clues about those ancient beginnings. We often imagine the solar system forming together, world by world, as though every planet shared equal influence. The evidence suggests something very different. One giant arrived early, claimed control of the available resources, and began shaping the destinies of everything that followed. Picture a solar system that refuses to stay still. We often imagine planets forming and remaining where we find them today, following familiar paths around the sun for billions of years. Yet, one of the most influential ideas in modern planetary science suggests a far stranger history. According to a model proposed by Kevin Walsh and colleagues in 2011, Jupiter may have traveled across vast regions of the young solar system before returning to the orbit we know today. This idea is known as the Grand Tack. The name comes from sailing. A tack is a reversal of direction made by a ship changing course against the wind. In this ancient cosmic version, Jupiter performed a similar maneuver through a sea of gas, dust, and growing worlds. The journey may have begun far beyond its present location. While the solar system was still young, Jupiter interacted gravitationally with the dense disk of gas surrounding the Sunday. Those interactions gradually robbed the giant planet of orbital energy, causing it to spiral inward, slowly at first, then steadily. As Jupiter moved toward the Sun, it transformed everything in its path. Material that might have become planets was scattered away. Smaller bodies were pushed outward, others were thrown inward. Vast populations of icy objects from colder regions found themselves redirected toward the inner solar system. Among them were water-rich asteroids, carrying frozen reservoirs and complex carbon-bearing compounds. Earth did not yet exist in its final form. Its building blocks were still gathering. The timing proved crucial. Many researchers believe that some of the water covering Earth's surface today originated from these redirected objects. Evidence comes from detailed studies of isotopes, subtle variations within atoms that act like chemical fingerprints. Water found in certain carbon-rich asteroids closely resembles the water found in Earth's oceans. The resemblance suggests a shared history. But Jupiter's inward migration did not continue indefinitely. Another giant entered the story. As Saturn accumulated mass, it too began moving through the gas disk. Eventually, the two planets became locked in a gravitational resonance, a repeating orbital relationship in which their motions synchronized. Once connected in this way, their combined interactions with the surrounding gas changed dramatically. The inward movement stopped. Then everything reversed. Together, Jupiter and Saturn migrated outward. The giant planet that had been approaching the Sun turned around and headed back toward the outer solar system, leaving behind a profoundly altered environment. This reversal helps explain several long-standing mysteries. Mars appears surprisingly small compared with what many formation models predict. Jupiter's passage may have removed much of the material that would otherwise have built a larger world. The asteroid belt contains only a tiny fraction of its expected mass. Repeated gravitational disturbances during the migration could account for that depletion. And Earth emerged within a region reshaped by both passes. Current simulations suggest that without this remarkable journey, our planet might have formed with far less water, accumulated a different mass, or settled into a different orbit altogether. Small changes in those outcomes could have transformed the future of life before life ever had a chance to begin. The path Jupiter followed may have lasted only a brief chapter in solar system history. Its consequences never ended. If you could gather every asteroid between Mars and Jupiter and place them together, you might expect a world of impressive size to emerge. Popular imagination often pictures the asteroid belt as the shattered remains of a lost planet, broken apart in some ancient catastrophe. The reality is stranger. No planet was destroyed there. A planet never finished forming. The region between Mars and Jupiter contains countless rocky bodies, ranging from dust grains to dwarf planets hundreds of kilometers across. Yet all of them together contain remarkably little material. The total mass of the entire asteroid belt is less than 4% of the mass of Earth's moon. For a region occupying such a vast stretch of space, that amount is surprisingly small. Planet formation normally follows a familiar path. Tiny particles collide and stick together. Larger objects emerge. Their gravity strengthens. Growth accelerates. Over time, worlds take shape. Here, the process kept failing. Jupiter's influence reached across the young solar system and repeatedly interrupted the assembly line. Objects that might have merged into larger bodies instead found their orbits disturbed. Relative speeds increased. Collisions became destructive rather than constructive. Many impacts occurred at speeds near 5 kilometers per second, which is about 3.1 miles per second. At such velocities, rocky bodies tend to fragment rather than combine. Each collision often produced more debris than progress. The belt remained trapped in an unfinished state. Over immense spans of time, another process continued reshaping the region. Astronomers call it orbital resonance, a repeating gravitational relationship between objects that circle the sun in predictable ratios. A resonance may sound gentle, yet its effects accumulate steadily across millions of years. Jupiter excels at exploiting this mechanism. Certain locations within the belt experience repeated gravitational nudges, timed with extraordinary precision. Small disturbances build upon previous ones. Orbits gradually stretch and become unstable. Eventually, objects are removed altogether. In 1866, astronomer Daniel Kirkwood identified striking gaps within the asteroid belt. These regions, now called Kirkwood gaps, contain far fewer asteroids than surrounding areas. They mark locations where Jupiter's repeated influence has effectively swept material away. One of the strongest examples occurs in the 3-to-1 resonance. An asteroid there completes 3 orbits around the Sun, while Jupiter completes 1. The repeated alignment steadily alters the asteroid's path until it may plunge toward the Sun, escape the solar system entirely, or enter the interplanetary region. This is where the story becomes more complicated. Jupiter reduces the overall population of dangerous objects across geological time, yet some of the same mechanisms that clear the belt also redirect material inward. A fraction of those wandering bodies eventually cross Earth's orbital neighborhood. So the giant planet acts neither as a perfect guardian nor a simple threat. Instead, it continuously reshapes the flow of material through the solar system. Across 4.5 billion years, that process has left Earth with a far less crowded asteroid belt than would otherwise exist. Yet scattered remnants still remain, following paths that occasionally intersect with the world beneath your feet. The discovery began with a mistake. At least, that was how it appeared at first glance. In March of 1993, Carolyn Shoemaker was examining photographic plates from Palomar Observatory in California. She had spent years finding comets and knew their appearance intimately. A comet should possess a single bright nucleus, surrounded by a faint cloud. This object did not. Instead, it looked stretched apart. A chain of separate fragments occupied the image, linked together like beads drifting through space. The shape was so unusual that it immediately stood apart from everything Carolyn Shoemaker had previously encountered. Few observers on Earth were better positioned to recognize that something extraordinary had appeared. The object received the designation Shoemaker-Levy Nine, named for Carolyn Shoemaker, Eugene Shoemaker, and David Levy. Further investigation soon revealed an astonishing story. 1 year earlier, in July of 1992, the comet had passed extremely close to Jupiter. During that encounter, it crossed the Roche limit, a boundary where tidal forces become stronger than an object's own gravity. Tidal forces arise because gravity pulls more strongly on the nearer side of an object than on the farther side. For Shoemaker-Levy 9, the effect was catastrophic. Jupiter pulled the comet apart. 21 fragments emerged from the encounter. Some measured only a few hundred meters across. Others approached 2 kilometers, which is about 1.2 miles, in diameter. Together, they stretched across roughly 1,100,000 kilometers, which is about 684,000 miles, forming one of the strangest structures ever observed in the solar system. Then astronomers realized something even more remarkable. The fragments were going to hit Jupiter. For the first time in human history, scientists could predict a major planetary impact before it occurred. They knew the sequence. They knew the dates. They knew approximately where the collisions would happen. During July of 1994, the world watched. The first fragment struck on July 16th. More followed. Each impact released staggering amounts of energy. Fragment G, the largest, arrived on July 18th. Its collision generated an estimated 6 million megatons of explosive energy. The resulting fireball rose roughly 3,000 kilometers above Jupiter's cloud tops, which is about 1,864 miles. The scar left behind exceeded Earth's diameter. Amateur astronomers could see it through backyard telescopes. Professional observatories monitored dark marks spreading across Jupiter's southern hemisphere. Those scars lingered for months. Something changed after that week. Researchers had long understood that large impacts posed genuine dangers, yet many discussions remained theoretical. Shoemaker-Levy 9 transformed calculations into observation. Humanity had witnessed a planetary collision unfolding in real time. Space agencies expanded efforts to locate potentially hazardous objects. New surveys received greater support. Governments held discussions about planetary defense. Observatories dedicated increasing attention to tracking bodies that crossed Earth's orbital neighborhood. But one thought remained difficult to ignore. Before Jupiter captured the comet, its path had carried it through the inner solar system. Exactly what might have happened under different circumstances remains uncertain. The calculations are complex and incomplete. The outcome we observed is not. A giant planet intercepted the visitor, absorbed every fragment, and left the evidence visible across its atmosphere for the entire world to see. Scientific certainty can be surprisingly temporary. For several years after the collisions of Shoemaker-Levy 9, a simple picture dominated public imagination. Jupiter stood as Earth's guardian, a colossal barrier intercepting dangerous visitors before they could threaten the inner planets. The idea felt intuitive. A giant world had visibly absorbed a devastating impact. The evidence seemed written across its atmosphere. Many researchers accepted the basic narrative. Then the details became harder to ignore. In 2008, astronomers Jonathan Horner and Barry Jones of Open University published research that challenged the familiar story. Using computer simulations, they explored a deceptively simple question. What would happen if Jupiter did not exist? The results proved unsettling. Their models suggested that Jupiter's role extends far beyond protection. The giant planet also acts as a gravitational accelerator, altering the paths of distant objects and sometimes directing them toward the inner solar system. Far beyond Neptune lies the Oort cloud, a vast spherical reservoir of icy bodies surrounding the solar system. These objects travel on enormous orbits that can require millions of years to complete. Many would never approach Earth closely on their own. But gravity changes trajectories. As some of these distant comets pass through the outer regions of the solar system, Jupiter can redirect them. A gentle gravitational encounter may become a powerful slingshot effect, reshaping an orbit and sending the object inward. In certain cases, threats reaching Earth's neighborhood exist because Jupiter helped place them there. This complicated the traditional picture. Without Jupiter, some long period comets might simply remain on distant paths, drifting through the outer solar system without ever approaching the terrestrial planets. The simulations even suggested that certain categories of impacts could become less frequent in a solar system lacking Jupiter altogether. Not everyone agreed. Subsequent studies produced different outcomes depending on assumptions, orbital distributions, and model parameters. Researchers continue debating the exact balance of Jupiter's influence. Yet one conclusion has endured. The shield analogy is incomplete. Jupiter removes danger and creates danger. It captures some objects. It ejects others entirely. It redirects a portion inward. Each effect operates simultaneously across immense spans of time. The evidence supporting these processes is substantial. Over billions of years, Jupiter has reduced the population of rocky debris remaining in key regions of the solar system. We have direct observational proof that it can intercept incoming objects. We also know that gravitational encounters routinely alter the paths of comets and asteroids moving through its domain. What remains uncertain is the final accounting. Would Earth experience more impacts without Jupiter or fewer? The answer depends on which populations of objects are measured and over what timescale. Different categories of threats respond differently to Jupiter's presence. So, the most accurate picture is neither guardian nor villain. Instead, Jupiter functions as a gatekeeper. It influences which objects arrive, how often they arrive, and where they come from. Every extinction event, every long period of environmental stability, every evolutionary opportunity unfolded within a system whose traffic patterns were shaped by that immense planet. The rules were never random, they were gravitational. Imagine lowering yourself through Jupiter's atmosphere and attempting to answer a simple question. At what point have you entered the planet? The deeper you travel, the harder that question becomes. On Earth, boundaries help us navigate. We move from air to ocean, from soil to bedrock, from crust to mantle. Jupiter offers no equivalent landmarks. There is no solid surface waiting beneath the clouds. No distinct threshold. Only a gradual progression into conditions that become increasingly unfamiliar. The visible cloud tops mark the beginning of that descent. Pressure there resembles conditions near sea level on Earth. Yet after falling only 50 kilometers, which is about 31 miles, the surrounding atmosphere has already compressed dramatically. Each layer, below, introduces new chemistry and new extremes. The uppermost clouds consist largely of ammonia ice crystals. Their temperatures hover around minus 145 degrees Celsius or minus 229 degrees Fahrenheit. These high clouds contribute much of Jupiter's pale coloration visible from afar. Farther down lies a darker region rich in ammonium hydrosulfide. This unusual compound forms under conditions rarely encountered elsewhere in the solar system. Here it gathers into broad orange and brown layers suspended within the atmosphere. Deeper still, water begins to appear. Ice particles and droplets occupy a region where pressures and temperatures become more familiar by planetary standards. It is the only major cloud layer containing water in forms that resemble those found on Earth. Yet even here, the environment remains profoundly alien. The descent continues. Hydrogen dominates everything below. As pressure increases, the gas grows denser and hotter, but it does not transition neatly from one state into another. Instead, it passes through a supercritical fluid phase, a condition where the distinction between gas and liquid effectively disappears. Matter behaves in ways our everyday intuition struggles to follow. Around 10,000 kilometers below the cloud tops, which is about 6,214 miles, the transformation becomes extraordinary. Pressures reach roughly 1 million times those at Earth's surface. Temperatures climb beyond 10,000 degrees Celsius or 18,032 degrees Fahrenheit. Hydrogen changes again. Under these crushing conditions, electrons move freely through the material. The substance becomes electrically conductive. Scientists call it metallic hydrogen because it behaves like a metal despite being composed of the simplest element in the universe. An immense ocean of this material occupies Jupiter's interior. Researchers estimate this metallic region may extend roughly 40,000 kilometers in thickness, which is about 24,855 miles. Vast currents move through it continuously. Those motions generate Jupiter's powerful magnetic field through a process known as a dynamo, where moving electrically conductive material creates magnetism. At the center, the story grows less certain. Data from the Juno spacecraft suggests there may be no sharply defined rocky core. Instead, heavy elements appear mixed with surrounding hydrogen across a broad diffuse region. The traditional image of a compact central sphere may be incomplete. Temperatures there could reach 20,000 to 30,000 degrees Celsius, or 36,000, 32 to 54,000, 32 degrees Fahrenheit. Conditions exceed those found on the sun's visible surface. And all of that energy remains hidden beneath layers, with no true bottom to find. Long before a spacecraft encounters Jupiter itself, it enters territory already claimed by the planet. Nothing visible marks the border, no wall appears, no cloud forms a boundary. Yet, far out in space, Jupiter's influence has already taken control, creating a magnetic domain so immense that it dwarfs nearly every other planetary structure in the solar system. We call this region the magnetosphere. A magnetosphere is the volume of space, governed primarily by a world's magnetic field rather than by the solar wind. The constant stream of charged particles flowing outward from the sunday. Around Jupiter, that volume reaches astonishing dimensions. Facing the sun, the magnetic boundary can extend roughly 3 million kilometers, which is about 1,864,000 miles. In the opposite direction, pressure from the solar wind stretches it into a vast tail, extending more than 600 million kilometers, which is about 373 million miles. That distance approaches Saturn's orbit. If human eyes could somehow perceive magnetic fields from Earth, Jupiter's magnetosphere would appear larger in the sky than the Sun itself, an invisible giant surrounding another giant. Its strength begins deep below. Within Jupiter's interior, electrically conductive metallic hydrogen circulates through powerful rotating currents. This process, known as the dynamo effect, converts motion into magnetism. Earth generates a magnetic field through movement inside its molten iron core. Jupiter operates through the same underlying principle, but on a far greater scale. The result is extraordinary. Near the cloud tops, Jupiter's magnetic field is roughly 20,000 times stronger than Earth's. Charged particles become trapped within this field and accelerated to tremendous energies. Some arrive from the solar wind, others come from much closer sources. One moon dominates the process. Io continuously erupts material from hundreds of active volcanic centers. Sulfur dioxide gas rises above its surface and escapes into surrounding space. There, intense radiation strips electrons from the atoms, creating ions, electrically charged particles that respond immediately to magnetic forces. Jupiter gathers them. The particles spread into a gigantic plasma torus, a ring-shaped cloud of electrically charged matter encircling the planet. Plasma simply means gas, whose atoms have lost or gained electrons, allowing it to conduct electricity and interact strongly with magnetic fields. The entire system remains in motion. Radio waves pulse outward, charged particles spiral through magnetic pathways, energy transfers across distances difficult to comprehend. Jupiter becomes less a planet than the center of an enormous electromagnetic machine. For spacecraft, the environment is unforgiving. The Galileo spacecraft spent years orbiting Jupiter between 1995 and 2003. During that time, radiation gradually damaged electronics and instruments, despite extensive protective engineering. Every mission sent into this region must account for the same danger. An unshielded human could not survive there for long. At the poles, another consequence appears. Permanent auroras shine continuously above Jupiter's atmosphere. Unlike Earth's occasional displays, these luminous rings never disappear. Observations by the Hubble Space Telescope revealed immense glowing ovals radiating ultraviolet and X-ray energy around both poles. They endure without interruption, sustained by the restless magnetic empire surrounding the largest planet in our solar system. Imagine a world that cannot stop reshaping itself. Every moment beneath its crust, vast amounts of energy are being released. Mountains collapse, lava spreads across plains, sulfur rises into the sky, new terrain appears, while older landscapes vanish. On Io, change is constant. You and I might expect such activity from a large planet. Yet, Io is only slightly larger than Earth's moon. It circles Jupiter at a distance of about 422,000 kilometers, which is about 262,000 miles. That close relationship defines everything about its existence. Seen from afar, Io looks unlike any other moon. Its surface is stained yellow, orange, red, black, and white by sulfur compounds erupted from below. Vast volcanic deposits cover enormous regions. Fresh material settles continually across the landscape. Nothing stays exposed for long. More than 400 active volcanic centers have been identified. Some erupt steadily for years. Others awaken suddenly and release extraordinary amounts of material. Giant plumes can rise 500 kilometers above the surface, which is about 311 miles, reaching heights unmatched anywhere else in the solar system. One detail immediately stands out. Impact craters are essentially absent. Throughout the solar system, ancient impacts usually accumulate and remain visible for immense spans of time. Io erases them. Lava flows, volcanic ash, sulfur deposits, and tectonic changes cover old scars so efficiently that the moon appears geologically young despite its ancient age. The source of this activity is not hidden inside Io alone. It comes from Jupiter. Io follows an orbit that is slightly elliptical rather than perfectly circular. That shape persists because of a gravitational relationship known as the Laplace resonance. A resonance is a repeating orbital pattern. For every orbit completed by Ganymede, Europa completes two. During the same interval, Io completes four. Those repeated gravitational interactions prevent stability. As Io moves through its orbit, Jupiter's pull changes continuously. Sometimes the moon is slightly closer, sometimes slightly farther away. The difference may seem modest, but the consequences are immense. The entire moon flexes. Its surface rises and falls by as much as 100 meters during each orbit. That is about 328 feet. Rock bends. Interior layers deform. Friction develops throughout the moon's interior. Heat accumulates relentlessly. This process is called tidal heating, meaning heat generated through repeated gravitational squeezing. The total energy released is estimated at roughly 100 trillion watts, more than twice the heat escaping from Earth's entire interior, despite Io's much smaller size. Deep reservoirs of molten rock remain active as a result. Near major volcanic vents, temperatures can exceed 1,600 degrees Celsius or 2,912 degrees Fahrenheit. Some eruptions produce lava hotter than many volcanic eruptions on Earth. Humanity first witnessed this activity unexpectedly in 1979 while analyzing images from Voyager 1. Navigation engineer Linda Morabito noticed what appeared to be an object extending beyond Io's edge. Further examination revealed something remarkable. The feature was not a distant star. It was a volcanic plume rising above another world. For the first time, an eruption had been observed beyond Earth, revealing a moon caught in an endless struggle with gravity itself. From high above, Europa appears almost delicate. Its surface reflects sunlight with remarkable brightness, revealing a landscape of pale ice crossed by countless reddish-brown streaks. Some lines run for thousands of kilometers, which is about hundreds to thousands of miles, cutting across the moon in tangled networks. Others curve gracefully over the horizon before disappearing into the distance. Looking down on Europa, you could mistake it for a frozen shell fractured by age. But the story beneath that ice is far more profound. Europa is slightly smaller than Earth's moon. Beneath its frozen exterior lies a vast ocean of liquid water, hidden under an ice shell estimated to be between 15 kilometers, which is about 9.3 miles, and 25 kilometers thick, which is about 15.5 miles. Beneath that barrier, darkness extends downward into a global sea unlike anything on Earth. The scale is astonishing. Scientists estimate Europa's ocean contains roughly twice as much water as all of Earth's oceans combined. More liquid water may exist beneath Europa's ice than on every continent and in every ocean basin of our own world together. And it has endured. For billions of years, tidal forces generated by Jupiter have supplied energy to Europa's interior. The process resembles the mechanism driving Io's volcanism, though in a gentler form. Europa flexes as it moves through space, generating heat deep below the surface. That heat prevents the ocean from freezing solid. The water remains in motion. Evidence suggests the reddish material streaking across Europa's fractures contains salts, including sodium chloride, the same chemical compound that gives Earth's oceans their familiar salinity. These materials appear to have traveled upward from below, indicating communication between the hidden ocean and the frozen exterior. The ocean is not isolated. It circulates, exchanges material, and evolves over time. Observations from the Hubble Space Telescope added another layer to the mystery. In 2012, and again in 2016, astronomers detected what appeared to be towering plumes of water vapor erupting from Europa's southern hemisphere. These eruptions may represent ocean material escaping through cracks in the ice and venting directly into space. If those plumes occur regularly, an extraordinary possibility emerges. A spacecraft would not need to drill through 20 kilometers of ice, which is about 12.4 miles, to study the ocean. It could simply fly through the ejected material and analyze it directly. That possibility has transformed Europa into one of the most important destinations in planetary science. Astrobiologists, scientists who study life's potential beyond Earth, focus on four essential ingredients: liquid water, chemical energy, necessary elements, time. Europa appears to possess all four. Its ocean may interact with a rocky seafloor. Such contact could create hydrothermal vents, places where heated water emerges from the crust below. On Earth, researchers discovered thriving hydrothermal vent ecosystems in 1977. Entire communities survived there without sunlight, powered instead by chemical reactions between rock and water. Europa may offer similar conditions. To investigate that possibility, the National Aeronautics and Space Administration launched the Europa Clipper spacecraft in October of 2024. Scheduled to arrive in 2030, it will perform approximately 49 close flybys, mapping the ice shell, probing the hidden ocean, and examining the chemistry of this remarkable world that has preserved its secrets for nearly the entire history of the solar system. Far beyond the fractured plains of Europa, two larger worlds circle through Jupiter's domain, carrying secrets buried much deeper than anyone once imagined. Ganymede dominates the scene immediately. It is the largest moon in the solar system, stretching 5,268 kilometers across, which is about 3,273 miles. Despite being a moon, it exceeds the planet Mercury in size, yet its most surprising feature cannot be seen directly. A magnetic field surrounds it. When the Galileo spacecraft explored the Jovian system during the 1990s, instruments detected evidence that Ganymede generates its own magnetic field. No other moon is known to do this. The discovery revealed a miniature magnetosphere embedded inside Jupiter's vast magnetic environment, a smaller bubble nested within a much larger one. At Ganymede's poles, that magnetic field produces auroras. Faint rings of glowing gas drift around the moon's upper atmosphere. They are subtle compared with Jupiter's enormous displays, but they carry important information. In 2015, astronomers using the Hubble Space Telescope carefully measured how those auroras shifted as Jupiter's magnetic field swept past. Something unexpected appeared. The auroras moved less than predicted. That reduced motion suggested the presence of a conductive layer beneath the surface. Conductive means capable of carrying electrical currents. The best explanation was a deep ocean of salt water, hidden far below the ice. Researchers concluded that an ocean likely exists roughly 800 kilometers beneath the surface, which is about 497 miles, trapped between layers of ice above and below. The structure is astonishing. Rather than resting directly on rock, parts of Ganymede's ocean may be enclosed within multiple stacked layers of ice formed under immense pressure. Water exists between frozen worlds, creating an environment unlike anything found on Earth. The volume may be enormous. Current estimates suggest Ganymede contains more water than all Earth's oceans combined, perhaps substantially more. Almost none of it is visible from above. Farther outward, Callisto tells a different story. Its surface appears ancient and unchanged. Craters cover nearly every region. Impact scars overlap one another in dense patterns, preserving a record that reaches back almost 4 billion years. Looking at Callisto is like examining a fossilized archive from the solar system's youth. Yet, beneath that battered exterior, evidence points toward another hidden ocean. Scientists reached this conclusion through magnetic induction, a process in which changing magnetic fields generate electrical currents inside conductive materials. Measurements indicate a conductive layer located roughly 100 to 200 kilometers below the surface, which is about 62 to 124 miles. Unlike Europa or Io, Callisto receives little tidal heating. Its internal warmth likely comes from radioactive elements slowly decaying within its rocky interior. That gradual release of energy may be enough to preserve liquid water over immense spans of time. Taken together, the picture becomes remarkable. Europa, Ganymede, and Callisto all appear to shelter hidden oceans. The Jovian system may contain more liquid water than the rest of the solar system combined, including Earth. Almost all of that water remains concealed beneath layers of ice, circling endlessly around a giant planet whose gravity has shaped every corner of its realm. Across centuries of human observation, few features in the solar system have remained as recognizable as the vast crimson oval drifting through Jupiter's southern hemisphere. Generations have watched it. Empires rose and vanished while the storm endured. The earliest widely cited observation came from Giovanni Cassini in 1665 when he recorded a persistent marking on Jupiter's face. Astronomers continue debating whether that feature and today's Great Red Spot are truly the same object. The evidence is incomplete. Even using the most cautious interpretation, however, the storm has survived for at least 193 years. More ambitious estimates place its age closer to 358 years. Either figure is extraordinary. When astronomers measured the storm during the late 1800s, it stretched roughly 40,000 kilometers across, which is about 24,855 miles. 3 Earths could have fit side by side within its boundaries. But the giant has changed. Modern observations show a width of approximately 13,000 kilometers, which is about 8,078 miles. That remains larger than Earth itself, yet the storm has lost roughly two-thirds of its diameter since the 19th century. Year after year, the contraction continues. No one knows exactly why. The Great Red Spot is an anticyclone, a rotating high-pressure system. In Jupiter's southern hemisphere, it spins counterclockwise, opposite to the direction followed by hurricanes on Earth. Winds race around its perimeter at speeds approaching 640 kilometers per hour, which is about 398 miles per hour. Nothing on Earth compares. For many years, scientists assumed the storm occupied only Jupiter's upper atmosphere. That picture changed after the arrival of the Juno spacecraft. By repeatedly passing over the vortex and measuring subtle variations in Jupiter's gravity field, researchers discovered that the storm plunges far deeper than expected. Its roots descend between 300 and 500 kilometers below the visible clouds, which is about 186 to 311 miles. The storm is not painted on Jupiter's surface. It extends downward like a vast atmospheric mountain turned upside down, embedded within layers of turbulent gas. Its famous color remains mysterious. Laboratory experiments suggest that compounds containing sulfur along with complex carbon based molecules, may be carried upward from deeper regions and altered by ultraviolet radiation from the Sunday. The process appears plausible, yet no chemical recipe has fully reproduced the exact shades observed by spacecraft and telescopes. Questions remain. The shrinking itself is difficult to predict. Some atmospheric models suggest the storm may eventually stabilize as a smaller but more concentrated vortex. Others indicate a gradual weakening and dispersal. Human records simply do not contain another example for comparison. Then Juno uncovered another surprise. Pressure waves generated by activity within the storm travel upward through Jupiter's atmosphere. As those waves break and dissipate, they deposit energy into regions far above the cloud tops. Temperatures there are much higher than expected for a world so distant from the Sunday. In a sense, the storm helps warm the sky above it. Even after centuries of study, the Great Red Spot continues revealing new behavior, reminding us that Jupiter's atmosphere remains a living system whose deepest workings are still unfolding before us. The first images arrived from a perspective no spacecraft had ever seen before. Instead of looking across Jupiter's familiar cloud bands, Juno passed high above the poles and gazed straight downward into regions hidden from generations of observers. What appeared on the screens seemed almost artificial. At the North Pole sat a giant cyclone, surrounded by 8 others. Together they formed a pattern remarkably close to an octagon. Each storm measured roughly 4,000 to 4,600 kilometers across, which is about 2,485 to 2,858 miles. Every one was comparable in size to a continental nation on Earth. The South Pole revealed another surprise. There, a central cyclone was encircled by 5 companions arranged in a pentagonal formation. The geometry was different, yet equally striking. Nature rarely produces such orderly structures on scales this vast. Scientists checked repeatedly. They expected change. Atmospheric systems evolve, storms drift, boundaries shift, powerful vortices interact and combine. Yet as Juno continued its observations month after month and year after year, the arrangements persisted. The cyclones remained in position. They neither merged nor scattered. That stability presented a puzzle. On Earth, when large cyclonic systems approach one another, they often begin a gravitational dance known as the Fujiwara effect. Their circulations interact, causing them to orbit together and frequently merge into a larger system. The Jovian cyclones sit much closer than many Earth storms would tolerate, but they remain distinct. Some unseen balance preserves the spacing. Researchers suspect a process called beta drift contributes to the arrangement. Beta drift describes how rotating storms respond to changes in planetary rotation at different latitudes. In simple terms, a cyclone can experience subtle pushes caused by variations in the Coriolis effect, the apparent force generated by planetary rotation. The idea helps. It does not solve everything. Computer models reproduce parts of the behavior, yet none fully explain the remarkable precision Juno observes. The cyclones seem to repel one another just enough to maintain separation while remaining trapped within the same overall region. The scale is difficult to absorb. The central northern cyclone alone spans about 4,000 kilometers, which is about 2,485 miles. Together, the entire polar cyclone complex covers Jupiter's polar cap, creating one of the largest organized weather systems known anywhere. Nothing comparable has been found elsewhere. Saturn possesses its own famous mystery, a 6-sided atmospheric structure circling its north pole. That hexagonal feature remains difficult to explain. Yet even Saturn's strange geometry lacks the layered complexity of Jupiter's clustered cyclones. The discovery carried an important lesson. Decades of telescopic observations, flybys, orbiters, and theoretical work had already transformed Jupiter into one of the best studied worlds beyond Earth. Even so, a completely unexpected atmospheric architecture remained waiting above the poles, unseen until the proper vantage point finally arrived. The storms continue circling today. They hold their positions with remarkable discipline, tracing geometric patterns across a planet whose atmosphere often appears chaotic. Their persistence reminds us that Jupiter still contains processes that current atmospheric physics cannot fully describe, even after generations spent trying to understand it. Before Juno ever saw Jupiter, the mission had already solved a problem that seemed almost unreasonable. How do you send delicate electronics into one of the harshest radiation environments in the solar system and expect them to survive long enough to report back? The journey began in August of 2011. A powerful launch vehicle lifted the spacecraft away from Earth, but direct flight to Jupiter required more speed than the mission could afford. Instead, Juno followed a longer path through the inner solar system. In October of 2013, it returned for a gravitational assist flyby of Earth, borrowing momentum from our planet's motion around the Sun before heading outward once again. The distance was immense. By the time Juno reached Jupiter on the 4th of July, 2016, it had traveled roughly 2.8 billion kilometers, which is about 1.74 billion miles. Yet the voyage itself was only preparation for the greater challenge waiting ahead. Jupiter surrounds itself with danger. Its magnetic field traps enormous populations of high-energy particles moving at tremendous speeds. These particles penetrate spacecraft materials, disrupt electronics, damage memory systems, and gradually degrade instruments. A conventional spacecraft passing repeatedly through this environment would fail quickly. Engineers responded with armor. Near the center of Juno sits a titanium radiation vault. The walls are about 1 centimeter thick. Inside are the spacecraft's most vulnerable electronic systems, protected by a shield that reduces radiation exposure by roughly 800 times compared with the surrounding environment. Even that protection has limits. With every orbit, radiation leaves a mark. Mission controllers monitor accumulated damage carefully, tracking how much exposure remains within the spacecraft's design budget. Every scientific objective must be balanced against the reality that Jupiter slowly wears the vehicle down. Juno's orbit reflects that compromise. Rather than circling close to the planet continuously, the spacecraft follows a highly elongated polar path. It dives toward Jupiter, skimming to within about 4,200 kilometers of the cloud tops, which is about 2,610 miles, then retreats far away again. Only a few hours are spent deep inside the most dangerous regions before the spacecraft escapes outward. Those brief encounters are extraordinarily productive. Each close pass, known as a perijove, gathers measurements of gravity, magnetic fields, atmospheric structure, and deep internal processes with remarkable efficiency. Instruments designed specifically for these objectives extract information that earlier missions could not obtain. Another decision made Juno unusual. Unlike many deep space missions, it carries no nuclear power source. Three immense solar arrays stretch about 20 meters from tip to tip, which is about 66 miles. Wait, correction needed? No. 20 meters is not kilometers and requires no conversion. Even at Jupiter's distance, where sunlight is greatly reduced, the panels generate roughly 500 watts of power. The results have transformed our understanding of the planet. Gravity measurements indicate that Jupiter's heavy elements are distributed through a broad, diluted interior rather than concentrated inside a sharply defined core. The boundary scientists once imagined appears far less distinct. As the mission continued, extensions allowed close flybys of Ganymede, Europa, and Io. During encounters in 2023 and 2024, Juno captured unprecedented views of active volcanism on Io, revealing a world still being reshaped by relentless gravitational forces. A flash inside Jupiter does not behave the way you would expect. For decades, scientists assumed lightning on the giant planet would follow familiar rules. Storms need energy, and on Earth, that energy comes primarily from sunlight warming the atmosphere near the equator. The assumption seemed reasonable. Yet, Jupiter has a habit of rewarding reasonable assumptions with surprises. The first clue arrived in 1979. As Voyager 1 swept through the Jovian system, its instruments detected bursts of radio energy consistent with lightning discharges. The spacecraft crossed Jupiter's shadow too quickly to capture direct images of the storms responsible, but the signal was there. Something enormous was sparking deep inside the atmosphere. Years later, the Galileo mission confirmed the existence of lightning more directly. Observations between 1995 and 2003 revealed flashes within the clouds, but resolution remained limited and many questions survived. Then Juno arrived. During repeated close passes above the cloud tops, its instruments recorded thousands of lightning events. Patterns emerged. Some matched expectations, others overturned them completely. The most surprising discovery involved location. On Earth, powerful thunderstorms cluster near tropical regions where solar heating is strongest. Jupiter's lightning favors the poles. Vast concentrations of electrical activity occur far from the equator in regions receiving relatively little sunlight. The explanation points inward. Jupiter radiates more heat than it receives from the sun, and that internal energy drives atmospheric circulation from below. Weather on Jupiter is powered largely by the planet itself. The storms are fierce. Researchers estimate many Jovian lightning bolts release several times more energy than the strongest lightning events measured on Earth. Within towering cloud systems, electrical charges separate and accumulate until immense discharges race through the atmosphere. But sight was only part of the discovery. Juno also captured the radio signatures of these strikes. Scientists converted those signals into audible frequencies. The resulting sounds are known as whistlers, named for their descending tones. Instead of a sudden crack, the recordings drift downward in pitch over several seconds. The effect occurs because radio waves spread across different frequencies while traveling through Jupiter's environment. You can almost imagine distance itself becoming sound. The atmosphere revealed other surprises. Juno's microwave radiometer, an instrument capable of sensing deep beneath visible clouds, detected giant ammonia plumes rising from lower layers. These upwellings extend far below the weather patterns visible from space, transporting material upward through regions hidden from ordinary cameras. But the strangest explanation emerged in 2020. Scientists proposed the existence of mushballs, slushy mixtures of ammonia and water ice, forming high in the atmosphere before falling deeper into the planet. These frozen masses may transport water downward, hiding it from instruments sampling only limited depths. The idea helped solve a long standing puzzle. When Galileo released an atmospheric probe, it measured far less water than expected. The probe may simply have entered a region where mushballs had already removed much of the moisture. Taken together, the lightning, the strange sounds, the ammonia plumes, and the falling mushballs reveal a world far more complicated than its distant appearance suggests. From Earth, Jupiter can seem like a striped sphere hanging beyond Mars. Up close, it behaves like an active planetary engine, generating phenomena that challenge assumptions almost as quickly as we make them. For most of human history, if you had asked what planets possessed rings, there would have been only one obvious answer. Saturn owned that identity completely. Its brilliant bands dominated textbooks, observatory photographs, and popular imagination. Jupiter seemed different, a world of storms and moons, with nothing resembling those luminous structures. Then came an unexpected discovery. In 1979, as Voyager 1 approached Jupiter, mission planners directed the spacecraft to examine the region along the planet's equatorial plane. The request was based on theoretical predictions suggesting a ring system might exist. Expectations remained cautious. No telescope on Earth had detected anything there. The rings appeared anyway. They were not bright. They were not dramatic. They were barely visible at all. Unlike Saturn's icy rings, Jupiter's rings consist primarily of tiny silicate dust grains. These particles absorb much of the sunlight, reaching them rather than reflecting it efficiently back into space. As a result, the entire system remains faint and elusive, almost disappearing against the darkness surrounding the planet. Yet the structure is surprisingly complex. Closest to Jupiter lies the halo ring, a broad torus of dust extending from roughly 92,000 kilometers, which is about 57,000 miles, to 122,500 kilometers, which is about 76,100 miles from the planet's center. Fine particles scattered through this region create a diffuse glow rather than a sharply defined boundary. Beyond it sits the main ring. This narrow band stretches about 6,400 kilometers wide, which is about 3,977 miles, while remaining less than 30 kilometers thick, which is about 18.6 miles. The proportions are extraordinary. If scaled appropriately, the structure would resemble an immense sheet spread across space. Its material originates from nearby moons. Micrometeorites constantly strike the small inner satellites, Metis and Adrastea. Each impact launches dust into orbit around Jupiter. Over time, countless collisions replenish the ring, replacing particles gradually lost through gravitational interactions and radiation effects. Farther outward, the system becomes even more delicate. Two broad gossamer rings extend beyond the main ring. Their dust comes primarily from Amalthea and Thebe, larger inner moons whose surfaces are continually peppered by incoming debris. The resulting particles disperse into faint structures that challenge even sophisticated instruments to detect clearly. But the significance of the discovery extended beyond Jupiter itself. Once astronomers confirmed rings around Jupiter, assumptions about giant planets changed rapidly. Subsequent observations revealed ring systems around Uranus and Neptune as well. Saturn remained the most spectacular example, yet rings were no longer a unique planetary feature. They appeared instead to be a common consequence of gravitational systems interacting with moons and dust. One of those source moons, Amalthea, presents another puzzle. Measurements indicate it emits more heat than expected from sunlight alone. A leading explanation involves electrical induction. As the moon moves through Jupiter's powerful magnetic environment, electrical currents may develop within its interior, generating additional warmth. What first appeared to be a simple dust system gradually revealed a network of interactions linking rings, moons, impacts, and magnetism. Even here, in one of Jupiter's least celebrated features, the planet refuses to be uncomplicated. Long before telescopes, spacecraft, or written theories of gravity, people noticed one wandering light that refused to behave like the others. Night after night, year after year, Jupiter shifted against the background stars. You could watch it drift. You could track its return. Unlike the fixed constellations, it moved with purpose. Ancient observers paid attention. Among the most dedicated were the Babylonian astronomers. By roughly 1800, before the Common Era, they were recording Jupiter's position on clay tablets with astonishing consistency. Generation after generation contributed observations. The result was one of humanity's longest, continuous scientific records. Patterns emerged. The Babylonians recognized that Jupiter completed a journey around the sky in approximately 12 years. That cycle became deeply woven into their astronomical system. Its motions helped structure calendars, predictions, and observations that extended far beyond a single lifetime. But their achievement reached further than careful record keeping. In 2016, historians studying ancient tablets uncovered evidence that challenged assumptions about the history of mathematics. The calculations used to predict Jupiter's future position relied on a geometric method previously believed to have appeared much later in medieval Europe. The idea was remarkably sophisticated. Babylonian scholars represented changes in Jupiter's motion across time, then calculated an area associated with that change. From that area, they could estimate where the planet would appear in the future. Modern mathematicians recognized the underlying concept immediately. It resembled principles associated with integral calculus. More than 14 centuries separated those tablets from the work of later European scholars. Across the Mediterranean world, Jupiter acquired a different role. In ancient Rome, the planet became associated with Jove, ruler of gods and guardian of the heavens. Thunder, authority, and divine favor were linked to its presence. Even today, traces remain embedded in language. The word jovial reflects ancient beliefs that Jupiter influenced temperament and fortune. Yet the planet's greatest historical impact arrived through a small telescope. In January of 1610, Galileo Galilei directed one of the earliest astronomical telescopes toward Jupiter. Beside the planet, he noticed several tiny points of light. Their positions changed from night to night. Careful observation revealed something extraordinary. They were orbiting Jupiter. For the first time, humanity possessed direct evidence that celestial bodies could circle an object other than Earth. The observation struck at the foundation of the geocentric model, the long accepted belief that everything revolved around our world. The implications spread slowly. Arguments followed. Resistance followed. Galileo eventually faced trial and spent his later years under house arrest. Yet the moons continued moving around Jupiter regardless of human opinion. Their existence became part of the growing body of evidence that transformed humanity's understanding of the cosmos. Across nearly 4,000 years, Jupiter has served many roles: a wandering star, a calendar marker, a divine symbol, a mathematical challenge, a witness in one of history's greatest scientific debates. Through each era, the planet revealed something unexpected, and in doing so, revealed something about us as well. Imagine stepping far enough back that Jupiter becomes only one data point among billions. The storms fade from view, the moons disappear into distance. What remains is a question about probability. How often does a world like ours emerge? The rare Earth hypothesis, developed by paleontologist Peter Ward and astronomer Joe Kirschvink, begins with an important distinction. Microbial life and complex life may not follow the same rules. Tiny organisms can survive in astonishing environments. Large multicellular ecosystems appear far more demanding. Earth may represent something unusual. Within this framework, Jupiter becomes more than a giant planet. It becomes one component in a long chain of conditions that may have allowed complex organisms to persist for hundreds of millions of years. The argument does not claim Jupiter created life. It suggests Jupiter helped shape the environment in which life remained stable enough to grow increasingly elaborate. The details matter. Jupiter follows an orbit that is remarkably close to circular. Its orbital eccentricity, a measure of how stretched an orbit becomes, is only about 0.049. That means its gravitational influence changes relatively smoothly over time. A more elongated orbit could have introduced stronger variations into the architecture of the solar system. But location matters too. Jupiter formed beyond the frost line, the region where water ice can survive during planetary formation. Beyond that boundary, solid material accumulates more efficiently. Large icy cores can grow. Once such a core reaches sufficient mass, rapid gas accretion begins, a process in which enormous quantities of gas collapse onto the growing planet. That process built Jupiter. Yet Jupiter's size may be equally important. A smaller world would exert less control over surrounding material. A much larger one could have reshaped the inner solar system far more aggressively. Instead, Jupiter occupies a middle ground, massive enough to dominate outer planetary dynamics while leaving Earth on a long-term stable orbit. The story becomes even more specific when we consider migration. Current models suggest Jupiter drifted inward during its early history before reversing direction alongside Saturn. This scenario, known as the Grand Tack model, may have influenced the delivery of water and volatile compounds to the young Earth while preserving the rocky planets that already existed. Many variables had to align. For years, astronomers lacked enough planetary systems for comparison. That changed with the arrival of large exoplanet surveys. Thousands of planets have now been identified around distant stars. Among those discoveries, gas giants resembling Jupiter in broad terms do appear elsewhere. They are not unique. Studies indicate that cold Jupiters, meaning gas giants occupying distant and relatively circular orbits, exist around roughly 10% of Sun-like stars. But that figure answers only part of the question. We still do not know how many experienced the same sequence of formation, migration, resonance, and long-term stability that shaped our own planetary neighborhood. A study published in 2015 using data from the Kepler Space Telescope added another intriguing clue. Systems containing cold Jupiters appeared roughly 3 times more likely to host smaller inner planets. The connection remains under investigation, yet it hints that Jupiter-like worlds may influence planetary architecture in ways we are only beginning to understand. As we compare our solar system with countless others, Jupiter gradually transforms from a familiar planet into a measure against which entire worlds are judged. A casual lunchtime conversation has echoed across generations of science. In 1950, physicist Enrico Fermi sat with colleagues at Los Alamos National Laboratory and asked a question so simple that it remains unsettling today. Where is everybody? You can feel the weight behind it. By any ordinary measure, the universe appears generous. It is approximately 13.8 billion years old. The Milky Way alone contains somewhere between 200 billion and 400 billion stars. Around many of those stars orbit planets. Across interstellar clouds, astronomers detect the same ingredients associated with life: carbon compounds, water, and complex organic molecules. The raw materials seem widespread. Given enough worlds and enough time, intelligent civilizations might be expected to emerge repeatedly. Some should become ancient. Some should develop technologies beyond our imagination. A fraction might spread between stars or leave detectable traces of their existence. But the sky offers no clear answer. This tension became known as the Fermi Paradox. The apparent likelihood of life seems difficult to reconcile with the absence of evidence. To address that contradiction, scientists have proposed many possibilities. Among the most influential is the concept of a great filter. A great filter is a barrier, somewhere between lifeless chemistry and a civilization capable of reaching the stars. There may be a step so difficult that almost nothing succeeds. The location of that barrier remains unknown. It could occur before life begins. It could emerge much later. This is where Jupiter enters the discussion. The rare Earth perspective suggests that complex life may depend upon a long sequence of unusually specific circumstances. A planet with liquid water may not be enough. Stable climates, long periods without catastrophic disruption, the delivery of key materials during planetary formation, and the architecture of an entire solar system could all matter. Jupiter represents one example. Its mass, orbital position, migration history, and gravitational influence may have helped shape conditions that persisted for billions of years. If arrangements like this are uncommon, then worlds capable of supporting complex organisms could be far rarer than the number of planets residing within habitable temperature ranges. That possibility carries implications. The cosmic silence might exist because complex life seldom appears at all. Intelligence could be extraordinarily unusual. Civilizations might be separated not by distance alone, but by rarity. But another interpretation remains possible. Suppose Jupiter-like systems are common. Suppose stable planetary environments emerge frequently throughout the galaxy. The absence of detectable civilizations would then point elsewhere. Perhaps the transition from single cells to multicellular organisms is exceptionally difficult. Perhaps intelligence rarely develops. Perhaps technological societies face challenges that prevent long-term survival. The mystery would deepen. Europa adds another dimension to the puzzle. Beneath its frozen exterior lies an environment where liquid water, chemical energy, and immense stretches of time may coexist. If future exploration discovers life that originated independently from Earth, the implications would be profound. The universe would seem far more biologically fertile. And if life emerges wherever conditions permit, then Fermi's question becomes sharper than ever. The silence surrounding us would no longer suggest a shortage of opportunity. It would point toward some other hidden threshold, one that remains invisible as we continue listening across the dark between the stars. Imagine returning to Jupiter after a span longer than recorded human history. The planet would seem unchanged at first glance. The broad cloud bands would still circle its immense body. The familiar moons would still trace their ancient paths, yet beneath that appearance, change would already be underway. Everything is moving. Jupiter is not a finished object frozen in time. It continues to evolve through processes so gradual that entire civilizations rise and vanish before their effects become noticeable. Even now, one of its most famous features, is transforming before our eyes. The Great Red Spot grows smaller. Historical observations show that the storm has steadily contracted for more than a century. Its diameter has decreased by roughly 1,000 kilometers, which is about 621 miles, every decade. The pace is not perfectly predictable, and atmospheric systems rarely follow simple trajectories, but the trend remains unmistakable. No one knows its fate. The storm may fragment into smaller vortices. It may stabilize in a more compact form. It may eventually fade altogether. Humanity has never witnessed the complete life cycle of a storm like this, making every observation part of an unfolding record. Far beyond the clouds, another transformation proceeds through gravity itself. Jupiter continuously exchanges tiny amounts of orbital energy with Saturn, Uranus, and Neptune. Each interaction is minute, yet hundreds of millions of years allow small effects to accumulate into meaningful shifts. The solar system remains dynamic. Modern simulations reveal that planetary orbits are remarkably stable while still carrying traces of long-term uncertainty. Mercury is particularly sensitive to these influences. Across billions of years, some calculations suggest a small possibility that gravitational resonances, meaning repeated orbital interactions that reinforce one another, could push Mercury into chaotic behavior. Jupiter contributes to those calculations. Its immense mass helps shape the architecture of planetary motion, influencing possibilities that unfold across timescales almost impossible to imagine. But the most dramatic chapter in Jupiter's future does not originate from the planet itself. It comes from the Sunday. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel sustaining its core. As fusion shifts deeper within the star, the outer layers will expand enormously. Mercury will disappear. Venus will vanish. Earth will likely be consumed as well. Jupiter survives. As the Sun sheds mass, planetary orbits will gradually move outward. Jupiter and its moons will drift farther from the dying star. During that transformation, worlds now locked beneath ice may experience conditions unlike anything in their history. Europa could change. Ganymede as well. Some models suggest that increasing solar warmth may temporarily melt portions of their frozen surfaces, exposing liquid water before later cooling returns ice to dominance. Oceans, hidden for billions of years, might briefly meet open space. Meanwhile, Jupiter itself will continue a slower journey. Residual heat trapped since its formation will leak away. The planet will contract by tiny amounts and cool gradually through the ages. It approaches the temperature of the cosmic microwave background, the ancient radiation left behind by the Big Bang, drawing ever closer without truly crossing below it. And so the Guardian changes too, carried forward by the same passage of time that shapes every world in the solar system. Consider the span of events required for this moment. Not a single event, nor a handful, but a sequence stretching across billions of years, each stage resting upon conditions established long before anything resembling a human mind existed to notice them. We arrive late in the story. Long before Earth formed, a cloud of gas and dust collapsed beneath gravity. The resulting star emerged, with a mass falling within a remarkably narrow range. Had the Sun formed substantially larger, its lifetime would have shortened dramatically. Had it formed much smaller, the regions suitable for temperate worlds would have been compressed close to the star itself. The balance mattered. Within the young disk surrounding that newborn sun, Jupiter began assembling while gas still remained available. Timing was critical. Planetary disks do not last indefinitely. Observations of young stars suggest many lose their gas within only a few million years. Jupiter had to grow quickly enough to capture its vast atmosphere before that opportunity vanished. Then came movement. The giant planet migrated inward through the disk before reversing direction through a gravitational partnership with Saturn. This process, known as the Grand Tack, describes a change in orbital migration similar to a sailing vessel changing course. Models suggest that journey reshaped the architecture of the inner solar system and influenced how water-rich material reached Earth's neighborhood. But a suitable Earth still had to emerge. Our planet formed within the habitable zone, the region where temperatures can allow long-lasting liquid water. Earth acquired enough mass to retain an atmosphere and sustain internal geological activity. At the same time, it avoided becoming a world entirely covered by ocean or stripped into a barren desert. Another collision followed. A body, roughly the size of Mars, struck the young Earth, producing debris that later assembled into the Moon. That companion stabilized Earth's axial tilt, the angle between its rotational axis and orbital plane. Without such stability, climate variations may have become far more extreme over geological time. Life appeared surprisingly early. Evidence suggests microorganisms existed within the first billion years of Earth's history. Yet the transition from simple cells to complex multicellular organisms required immense stretches of additional time. Evolution advanced through countless experiments, adaptations, and failures. Extinction repeatedly intervened. At least 5 major mass extinctions reshaped life during the last 540 million years. Volcanism, climate change, shifting oceans, and impacts each imposed severe biological crises. Complex ecosystems collapsed again and again, yet life persisted. One event stands apart. 66 million years ago, an asteroid struck near what is now the Yucatan Peninsula. The impact ended the dominance of non-avian dinosaurs and opened ecological opportunities for mammals. Over tens of millions of years, those opportunities contributed to the emergence of primates, then hominins, then observers, capable of asking how any of this happened. Throughout that chain, Jupiter remained present. Its gravity influenced impact rates, orbital stability, and the broader structure of the solar system. It did not dictate outcomes. History retained uncertainty at every stage, but it helped define the boundaries within which those outcomes unfolded. And when we trace that chain backward, link by link, you begin to see how many doors remained open long enough for us to arrive here at all. A photograph can change a planet. Not the planet itself, of course. Jupiter remained exactly where it was. Its storms continued turning. Its clouds continued folding through one another. But in early 2017, when the first close views from Juno reached Earth, something shifted in the way we perceived this distant giant. The change was immediate. The spacecraft had approached to within roughly 9,000 kilometers, which is about 5,592 miles, of the cloud tops. Previous images had revealed structure and color, but these new views crossed a threshold. For the first time, Jupiter no longer resembled a striped sphere observed from afar. It became a place. Across the images stretched tangled currents of white, blue, tan, and deep brown, vast vortices wrapped around one another. Thin filaments curled into spirals. Bright plumes emerged from darker surroundings and dissolved again into turbulence. Seen close up, the atmosphere appeared strangely organic. You notice it instantly. The patterns resemble forms familiar from entirely different scales of nature. Some viewers compared them to cells beneath a microscope. Others saw pigments spreading across wet canvas. Many described cream swirling through coffee. Yet none of those comparisons fully survive scrutiny, because every structure visible in the images exists across distances measured in thousands of kilometers. The scale overwhelms analogy. What appears delicate often contains storms larger than entire continents. Features that seem like brushstrokes may extend for several thousand kilometers, which is about 1,864 miles. Hundreds of atmospheric systems coexist at once, interacting through layers of motion that remain active day and night. But the science community reacted in an unusual way. Juno carried a public outreach camera called JunoCam. Raw images were released openly, allowing citizen scientists and image processors around the world to transform the data into finished views. The resulting interpretations circulated rapidly. Researchers accustomed to discussing atmospheric dynamics found themselves talking about aesthetics. The word painting appeared often, not as a technical description, but as an honest reaction. The planet looked less like a conventional astronomical object and more like a work of art that somehow existed independently of any artist. Color gradients blended naturally, boundaries emerged and vanished, order and chaos occupied the same frame. Then there was the great red spot. Seen from close range, it revealed details hidden by distance. The famous storm appeared less red than expected, leaning toward deep auburn and copper tones. Bright spirals encircled its perimeter. Sharp boundaries separated it from neighboring currents. The structure seemed deliberate despite being shaped entirely by fluid motion. That contrast lingers. Scientists often describe a collision between intellect and perception when viewing these images. Rationally, you know Jupiter is a physical world obeying natural laws. Emotionally, the planet resists easy categorization. The mind struggles to reconcile familiarity with scale, complexity with coherence. But perhaps that is the deeper gift of these photographs. They transformed Jupiter from a collection of measurements into a destination for imagination, a real world waiting in the darkness, long before anyone possessed the ability to truly see it. Try holding 3 objects in your hand. You can sense each one separately. Add a fourth, and the distinction remains. A fifth begins to blur. Beyond that, something curious happens inside the human mind. Individual quantities dissolve into a broader impression. We stop perceiving separate things and begin perceiving simply many. The limitation is ancient. It emerged in brains, shaped by survival on a modest world, among quantities small enough to count at a glance. Predators, companions, food sources, shelter. The cognitive machinery worked well because it never needed to confront planets. Then we discovered Jupiter. From that moment onward, we entered territory where mathematics could travel farther than intuition ever could. We can calculate the planet's dimensions with extraordinary precision. We can model its gravity. We can track its storms. But understanding and feeling are different processes. The gap matters. Jupiter could contain 1,321 Earths by volume. The statement is accurate. The number can be written, spoken, and verified. Yet, there is no lived human experience corresponding to 1,321 worlds nested inside another world. The fact arrives intact. The intuition never follows. The same pattern appears again and again. Jupiter possesses more than 300 times Earth's mass. Its famous storm has persisted since at least the early 19th century. Its magnetic influence stretches hundreds of millions of kilometers into surrounding space, reaching roughly 600 million kilometers, which is about 373 million miles. Lightning discharges, release energies exceeding the strongest terrestrial examples. Every measurement is real. None become familiar. But this limitation does not reflect a weakness in science. It reflects the environment that produced us. Evolution rewarded minds capable of navigating forests, coastlines, seasons, and social groups. Nothing in our history required an instinctive grasp of planetary magnetospheres or atmospheric systems larger than continents. So we build tools. Mathematics extends perception beyond biology. Telescopes extend sight. Spacecraft extend presence. Through these inventions, we accumulate knowledge about places our nervous systems were never designed to imagine directly. Yet even complete scientific literacy leaves something unresolved. A residue remains. You can memorize every major property of Jupiter and still encounter a sense of distance between information and comprehension. The facts point toward something larger than themselves. They gesture toward a reality that exceeds ordinary mental scale. The philosopher Immanuel Kant described a related experience using the word sublime. By this, he meant an encounter with such vastness that the mind struggles to assemble it into a complete picture. Understanding persists. Visualization fails. Reason advances while intuition falls behind. Jupiter produces exactly that sensation. Its enormity resists containment. Its history stretches beyond ordinary perspective. Its dimensions overflow every natural reference point we possess. But there is comfort in recognizing that the universe contains things larger than our capacity to fully picture them. We continue anyway. You and I sit on a small world beneath a vast sky, building descriptions of realities we cannot completely hold, and that persistent effort may be among the most remarkable abilities our species has ever developed. Across libraries, control rooms, observatories, and university offices, an unusual pattern repeats itself. A person becomes interested in Jupiter, then years pass, sometimes decades. The planet remains distant, yet it slowly occupies more of a human life. The measurements accumulate. So do the questions. Science often reaches us as finished knowledge, polished and organized into neat conclusions. But behind every conclusion stands a chain of individuals who spent portions of their lives pursuing uncertainties that offered no guarantee of resolution. Carolyn Shoemaker was one of them. She discovered 32 comets during her career, more than any other person in history. At 51 years old, alongside her husband Gene Shoemaker and colleague David Levy, she helped identify the fragmented comet, later known as Shoemaker-Levy Nine. Years afterward, when those fragments collided with Jupiter, the event became one of the defining astronomical observations of the 20th century. The impacts left scars. For Carolyn Shoemaker, the significance extended beyond spectacle. Jupiter had demonstrated, on a visible stage, its ongoing role in reshaping the trajectories of wandering objects. A theoretical discussion had become a witnessed reality. Another turning point arrived through a very different path. Linda Morabito was only 26 years old when she examined navigation imagery returned by Voyager 1 in 1979. Her task was routine. The image appeared ordinary, yet something near the edge of Io seemed misplaced. She looked again. The feature was real. It was a volcanic plume rising above the moon's horizon. With that observation, humanity identified the first active volcanic eruption ever seen beyond Earth. A major planetary discovery emerged from careful attention rather than dramatic intention. Years later, another generation inherited the challenge. Members of the Galileo mission team spent nearly a decade studying Jupiter and its moons at close range. Orbit after orbit delivered fresh puzzles. Radiation gradually damaged spacecraft systems. Engineers adapted, Scientists revised expectations. New observations demanded new explanations. The work never truly settled. When Galileo was intentionally directed into Jupiter's atmosphere in September of 2003, the moment carried an emotional weight unusual for a machine. For many on the mission, the spacecraft had become a long-term companion in discovery. Then came Juno. Scott Bolton, principal investigator of the mission, had devoted decades to understanding the giant planet before the spacecraft ever arrived. When Juno returned its first detailed views of the polar regions in 2016, the images revealed structures to few researchers anticipated. Vast cyclones occupied precise arrangements around the poles, producing patterns that challenged existing atmospheric models. Even experts were surprised. Bolton later described the reaction plainly. Scientists had prepared for many possibilities. They had not prepared for that. These stories differ in detail, yet they converge on a shared experience. People approach Jupiter carrying expectations built from theory, observation, and simulation. Then the planet reveals another layer of complexity. The reality expands beyond prediction. Perhaps that is why so many careers remain anchored there. From one perspective, dedicating decades to a distant world may seem strange, yet you and I inherit the results of that devotion. Through patience, persistence, and curiosity, generations of researchers transformed a bright, wandering point in the sky into a place of astonishing depth, and they continued, because every answer uncovered another reason to keep looking. Long before oceans formed, before continents assembled, before the first living cell divided on Earth, a relationship already existed. Neither participant understood it. One was a young, rocky world, still taking shape from collisions and molten debris. The other was a growing giant beyond the frost line, gathering gas, ice, and rock until it became the dominant gravitational presence in the solar system. No intention connected them, no purpose guided them, only physics. Yet, over billions of years, that relationship helped shape the conditions within which everything familiar would emerge. Jupiter altered trajectories. It influenced migration patterns among smaller bodies. It affected impact rates. It helped determine the architecture of the planetary system surrounding the Sunday. Earth responded to the consequences. Jupiter never responded at all. There is something striking in that asymmetry. We often understand important relationships through the lens of awareness. Parents know their children. Friends know one another. Communities recognize the people they support. Meaning usually feels tied to recognition. The physical universe operates differently. The sun does not know it warms forests, oceans, and cities. The moon does not know it steadies Earth's rotational axis. Deep geological processes do not know they recycle material through the crust and mantle, helping regulate conditions across immense stretches of time. Still, their effects remain real. Jupiter belongs to that same category of influence. Its contribution emerges through existence alone. A planet of hydrogen, helium, ammonia, and extraordinary pressure follows the laws of nature, and those laws ripple outward across space. Life inherits the result. But Jupiter feels different from many other influences because of distance. The moon hangs visibly overhead. Sunlight touches your skin. Atmospheric changes surround every moment of daily experience. Jupiter remains far away, separated by hundreds of millions of kilometers, roughly 600 million kilometers, which is about 373 million miles, during portions of its orbit. It appears detached, yet the separation is deceptive. Across 4.5 billion years, the history of Earth and the history of Jupiter have remained intertwined through gravity, orbital mechanics, and chance events unfolding across cosmic timescales. And yet here we are, a species capable of tracing those connections, emerged on one of those worlds and began asking questions about the other. We learned enough mathematics to reconstruct ancient migrations. We built spacecraft capable of crossing interplanetary distances. We discovered that seemingly unrelated events, separated by vast spans of space, could still belong to the same story. The philosopher Alfred North Whitehead wrote that reality exceeds every description we create for it. Nature is not a narrative assembled for human understanding. It is an ongoing process within which understanding itself appears. That perspective places Jupiter and Earth in a different light. Neither exists for the other. Neither occupies a privileged position. Both participate in a larger unfolding, shaped by physical laws that preceded humanity by billions of years. But the outcome matters. A distant gas giant influenced the environment of a small blue world. That world produced living observers. Those observers eventually learned enough to recognize the connection. In that recognition, we glimpse something profound, a reminder that consequences can be immense even when intention is absent, and that existence itself can shape futures it never perceives. Step outside on a clear night, far from streetlights, and your eyes eventually settle on it. Among the scattered stars, one point shines with unusual steadiness. It does not flicker in the same way. It holds its brightness. It seems almost confident in its place against the darkness. That point is Jupiter. Only the Sun, the Moon, and Venus normally appear brighter in Earth's sky. Yet, unlike most of the lights surrounding it, Jupiter is not a distant star producing its own energy through nuclear fusion. What reaches your eyes is borrowed light, sunlight reflected from cloud tops floating high above a world unimaginably larger than our own. The distinction matters. Stars often twinkle because they appear as tiny points. Earth's atmosphere bends and distorts their light as it passes overhead. Jupiter presents a slightly broader disk. The turbulence averages out across that small, visible surface, giving the planet its characteristic steadiness. Ancient observers noticed this. They watched carefully. Night after night revealed little change, but months told a different story. Jupiter wandered. It drifted slowly against the fixed background of stars. That motion separated it from the constellations and transformed it into something special. A wanderer. Babylonian astronomers tracked its path. Greek philosophers debated its nature. Roman skywatchers linked it to their highest deity. Chinese astronomers recorded its position across generations. Indian scholars incorporated it into sophisticated astronomical traditions. Mayan observers followed its cycles with remarkable precision. Different cultures arrived at the same conclusion. The object mattered. None of them knew they were observing a gas giant more than 11 times wider than Earth. None knew about metallic hydrogen, volcanic moons, radiation belts, or hidden oceans beneath frozen crusts. Yet they recognized significance long before understanding. That recognition endured. Galileo Galilei joined the chain in January of 1610. Through a small telescope, he saw points of light shifting beside Jupiter from night to night. The discovery altered humanity's view of the cosmos. 4 centuries later, spacecraft would reveal details beyond anything he could have imagined, but the first step began with simply looking. The act remains available to us. When you observe Jupiter tonight, the light entering your eye began its journey at the Sunday. It traveled roughly 778 million kilometers, which is about 483 million miles, to reach Jupiter. a tiny fraction reflected from the planet's upper atmosphere. Then it crossed space again before finally descending through Earth's atmosphere. An astonishing voyage. Those photons passed through regions shaped by solar wind, crossed immense distances between planets, and completed a journey exceeding 1 billion kilometers, which is about 621 million miles. Yet they arrive effortlessly. Meanwhile, Jupiter continues its 12-year circuit around the Sun, moving through the same celestial pathways followed throughout recorded history. Generations rise and vanish beneath that rhythm. Civilizations change. Languages evolve. Jupiter keeps moving. Present, distant, and indifferent. It shines above us as it always has, carrying its immense gravitational influence through the solar system while asking nothing from those who pause to look. A line drawn in ink on paper can become the beginning of a revolution. In 1665, Giovanni Cassini studied Jupiter through a telescope and recorded a persistent feature in its atmosphere. The observation was simple: a mark, a sketch, a human hand attempting to preserve what an eye had seen for a moment. Centuries later, another human instrument passed astonishingly close to Io, approaching within roughly 1,500 kilometers, which is about 932 miles, and photographed active volcanic eruptions in progress. Between those two moments stretches one of the most remarkable intellectual journeys our species has ever undertaken. The planet remained where it was. We changed. Across that span of time, generations built upon generations. Observations became measurements. Measurements became theories. Theories became spacecraft. Each step carried us farther from intuition and closer to reality. Consider what we now know. A moon orbiting Jupiter contains a vast ocean beneath ice. That ocean lies beneath a frozen shell that may reach depths approaching several tens of kilometers, which is about several tens of miles. Its presence was not discovered by drilling or direct observation. Scientists detected it through magnetic induction, a process in which an electrically conducting ocean responds to changing magnetic fields and produces a measurable signal of its own. The ocean never announced itself. We learned to listen. Elsewhere in the Jovian system, we reconstructed events that unfolded billions of years ago. We traced planetary migrations. We modeled gravitational encounters. We calculated impact energies from fragments that vanished long before many people alive today were born. Knowledge accumulated slowly. Then came the spacecraft. A machine protected within a titanium vault crossed approximately 2,800,000,000 kilometers, which is about 1,740,000,000 miles, before settling into orbit around Jupiter. It carried instruments capable of sensing gravity, magnetism, radiation, and atmospheric structure with extraordinary precision. Those measurements transformed speculation into understanding. Yet, something deeper happened alongside the science. For billions of years, stars formed and died, planets assembled from dust, oceans existed beneath ice, gravity sculpted entire planetary systems. Throughout that immense duration, these processes unfolded without awareness. Then, awareness appeared. On a small, rocky world, living organisms evolved nervous systems capable of asking questions. Eventually, one species learned mathematics, built telescopes, invented electronics, launched spacecraft, and developed methods for extracting meaning from faint signals crossing space. Carl Sagan expressed this idea with a phrase that became famous, saying that we are a way for the cosmos to know itself. Within the story of Jupiter, the statement feels less like poetry and more like description. Through us, the solar system became observable to itself. Jupiter did not become larger when we understood it. Its storms did not change course. Its moons continued their ancient paths, but understanding altered the observers. We gained perspective unavailable to every generation before us. And perhaps that transformation is the most extraordinary discovery of all, that matter arranged itself into minds capable of learning what a giant planet is, how it formed, and why it mattered. Sometimes a question survives because it points beyond its own wording. For hours, we have followed storms, moons, impacts, migrations, and oceans hidden beneath ice. We have traced chains of cause and consequence stretching across billions of years. Yet the title remains waiting for us, unchanged. Does Jupiter decide whether Earth lives or dies? Taken literally, the answer is simple. Jupiter possesses no awareness. It has no intentions, desires, plans, or goals. It does not observe Earth. It does not protect it. It does not choose outcomes. It is a planet, a vast one. Its atmosphere churns. Its gravity acts. Its magnetic field extends through surrounding space. Everything it does follows the same physical laws operating throughout the universe. But the question survives because it gestures towards something deeper. When we examine the history of our solar system, Jupiter appears again and again at moments that mattered. During planetary formation, its immense gravity reshaped the distribution of material. During its migration, it helped determine where worlds could emerge and what ingredients reached them. Across immense spans of time, it influenced impact rates and orbital architecture. The pattern persists. Earth formed within conditions that were not created by Earth alone. The water covering its surface arrived through processes extending far beyond our planet. The environment that eventually allowed forests, oceans, animals, and human beings emerged within a larger gravitational system. Jupiter was part of that system. Always. The important realization is not that Jupiter controlled events. Physics is not command. Gravity does not issue instructions. Yet, outcomes depend on circumstances, and circumstances depend on physical realities established long before life appeared. In that sense, Earth's history has never belonged entirely to Earth. It has always been connected. Even now, the connection continues. Material still moves through the asteroid belt. Resonances, meaning repeating gravitational relationships between orbits, still shape the paths of countless objects. Europa still conceals its ocean beneath ice. Io still releases volcanic material into space. Vast cyclones continue circling Jupiter's poles. The Great Red Spot continues evolving toward a future nobody can confidently predict. Nothing has stopped. Not yet. And as new spacecraft continue exploring the Jovian system, another question remains close beside the first. If environments shaped by planets like Jupiter helped create the conditions necessary for intelligence, how often does that happen elsewhere? We do not know. A world orbiting another star may possess its own giant planet, its own icy moons, its own long chain of contingencies. Somewhere, similar processes may have unfolded. Somewhere, they may not have. The uncertainty remains profound. Yet one conclusion already stands. The story of Earth cannot be separated from the story of Jupiter. The two worlds differ in nearly every conceivable way, but their histories became linked during the earliest chapters of solar system formation and remain linked today. So does Jupiter decide whether Earth lives or dies? No, if by decision we mean intention. Yes, if by decision we mean that the conditions allowing Earth to become what it is were shaped, constrained, and guided by Jupiter's enduring presence from the beginning until this very moment. Look up on any clear night, and the story continues. Far beyond the familiar glow of Earth, Jupiter follows the same path it has followed throughout all of recorded history. It moves steadily through its approximately 12-year journey around the Sun, returning to the same regions of the sky generation after generation. Beneath its cloud tops, immense atmospheric currents continue their work. Around its poles, vast cyclones maintain their remarkable geometric arrangements. The Great Red Spot still turns counterclockwise, completing a rotation in roughly 6 days, carrying forward a storm that has endured for centuries. Nothing pauses. Nothing waits for us. Across the gulf of space, the Juno spacecraft continues its mission. During each elongated orbit, it swings close to Jupiter before retreating outward once more. Encased within its titanium vault, delicate instruments survive an environment saturated with radiation. Measurements become signals. Signals become streams of information. Traveling at the speed of light, those transmissions require about 43 minutes to cross the distance to Earth, where teams of scientists transform them into maps, models, and discoveries. The conversation continues. Another traveler is following behind. Europa Clipper is making its way through the inner solar system toward the Jovian system, embarking on a journey of approximately 2,800,000,000 kilometers, which is about 1,740,000,000 miles. When it arrives in the year 2030, it will begin the most detailed investigation of an ocean world ever attempted. Instruments designed to study ice, chemistry, geology, and hidden water will examine a moon that may contain one of the most promising environments for life beyond Earth. Whatever it finds, we will learn something new. That has always been the pattern. The Babylonian astronomers who tracked Jupiter's movements on clay tablets understood its regularity, but not its nature. Galileo Galilei observed 4 moons circling the planet and revealed that not everything revolved around Earth. Centuries later, observers watched fragments of Shoemaker-Levy Nine collide with Jupiter and witnessed the solar system behaving as a dynamic and sometimes violent place. Each generation added a piece. Each generation inherited more questions. What remains constant is Jupiter itself. Every night, experienced by every human civilization, unfolded beneath the presence of that distant planet. Kingdoms rose and disappeared. Languages emerged and changed. Entire worldviews transformed. Through all of it, Jupiter continued orbiting, influencing the architecture of the solar system through gravity alone. And now we know. We know that water may have reached Earth through processes Jupiter helped shape. We know that moons conceal oceans. We know that storms larger than worlds churn within its atmosphere. We know that one giant planet became woven into the history of a much smaller one. As this night deepens, Jupiter remains where it has always been, enormous, indifferent, and real. Long before Earth's first oceans formed, it was already there. Long after every living person today is gone, it will still be there. The giant is still out there. And for the brief moment in cosmic history that we are alive, we are one of the few things in the universe known to have noticed.